In this video, we're going to work example problems where we're given the graph of a trig function, any of the trig functions, like shown here, and we want to write the corresponding equation for that function. Now, for each of these problems, the possibilities for the equation that we come up with are endless, because as we know, with this looks to be tangent or cotangent. Well, you can start with tangent and then shift it, flip it, and create a cotangent, right? Same idea with secant, cosecant, and sine and cosine. So what we want to do is the equation that we write, we want to make it as simple as possible. So ideally, no phase shifts, no shifting horizontally. That would be the first priority. And then from there, if possible, no flipping. Okay. So for this first example, we can see this is tangent, cotangent, one of the two. And we know that tangent is just the base tangent is this shape in this direction. Cotangent is in the opposite direction. And so this here it's the shape of cotangent. However, we can see that, the period of tangent and cotangent is pi, but this period here going from minus pi over 2 to pi over 2, that's an unshifted period of tangent. And so since the first priority is we want to avoid shifting, then what we're going to need to do is write this as tangent and flip it. So, okay, y is equal to, and then we can do, so the period is still pi, so we're not scaling x, minus tangent of x. Okay, so we've got an unshifted horizontal tangent. This isn't shifted vertically either. And the flipping allows us to go from this to this. Now, you might say, well, did we flip about the x or the y? Like, how do we know which one to flip? Well, it doesn't matter in the case of tangent because it's got odd symmetry. So it wouldn't matter. We're going to flip about the x. But if we did minus x, like because it's odd, tangent of minus x is equal to minus tangent x, so it doesn't matter anyway. Now, we're not done yet because we need to check the vertical scaling. So it gives us a point here. We can see at minus pi over 4, the function is equal to 2. Okay, now pi over 4 in degrees is, so we've got pi radians for every 180 degrees. So 4 divided by 180 is 45. So 45 degrees, we do a 45, 45, 90 triangle. This is 1, 1, root 2. Now, but minus pi over 4. So tangent in the fourth quadrant is opposite over adjacent. Tangent is negative. So, all right, tangent 45 is 1. So tangent of minus pi over 4, minus 45 is going to be minus 1. But since we've got a minus out front here, it's positive, but it's 2 here. So that means that this is going to be scaled up by a factor of 2 about the y-axis. And there we go. Okay, here we can see this is like secant, cosecant. And as far as the shifting goes, this is secant, right? Unshifted secant it has this going through the or x is equal to 0, like this. Whereas cosecant would be over here. Okay, so as far as shifting goes, it seems like we want to use secant here. Now, it gives us a full period here from minus pi over 4 to pi over 4, so that's pi over 2 in total. But we know that the base period of secant and cosecant is 2 pi. So So 2 pi was multiplied by what to give pi over 2? So the factor that was applied here was, let's see, pi over 2 times 1 over 2 pi. It was scaled down by 1/4. So we can start with, no, it would be 4x. Secant 4x. That gets us started. Now, there's no flipping or anything, no shifting. Now, as far as scaling about the y-axis, if there was any scaling, that would affect the kind of minimum point here, the local minimum point here, the local maximum point, but it's still just 1. That's what standard secant is, right? Because like if at x, secant at x is equal to 0 is going to be 1. Secant of 0 is going to be 1. So if it was scaled about the y-axis, this would be a different value here. There's no shifting about the horizontal axis. That we've accounted for the horizontal scaling. So that's it. Okay, let's see. It looks like hasn't been, this is a sinusoid that hasn't been shifted, like or a sine curve that hasn't been shifted horizontally, but vertically it has. It's gone down -1, so y is equal to, we can say, unshifted sine x -1. That gets us started. Okay, what about the period? The period's 2 pi, so it's not scaled about the x. We don't have to do any flipping or anything. What about the amplitude? It's going from up and down 1, so this is it. Okay, so this looks like a cosecant shape, unflipped cotangent, and it also has the phase characteristics of cotangent, right? Cotangent has, before it's shifted, it has the horizontal or the vertical asymptotes going from 0 and then out a period. So we can see the period here is pi over 3. But we know the period of tangent and cotangent is pi, the standard period. So we've got pi was multiplied by something to give pi over 3. So what was it multiplied by? Pi over 3 times 1 over pi. It was multiplied by 1/3. So, okay, we can start with y is equal to cotangent 3x. All right, now let's see. A quarter of the way through a period, you've got, so pi over 3 divided by 1, 2, 3, divided by 4 is pi over 12. So at pi over 12, what is pi over 12 in degrees? So pi radians, 180. Okay, 180 divided by 12 is 15. So pi over 12 radians is 15 degrees. That's not one of the special angles. So let's see. Let's put this. Oh wait, well no, that's not right. So it's gonna, we put it into the function. So pi over 12 times 3. 3 times pi over 12 is pi over 4, which was 45 degrees, which we know is going to be 1, right? We had the unit circle, or the 45, 45, 90. Cotangent is adjacent over opposite. That's just 1 as well. This is positive. We put in positive pi over 12, so it's cotangent positive pi over 4. So it's just 1. And that's what we get here. So there's no scaling about the y-axis. So we've accounted for the scaling about the x-axis. There's no horizontal shifting. This is, okay, so yeah, there we go. Okay, so this is either secant or cosecant, and as far as the horizontal shifting, this would be cosecant. because with no shifting, secant goes through the x is equal to 0, the y-axis. But cosecant is like this. Now they show us a full period. With the period going from here to here is 2 pi, so no horizontal scaling. All right, so we can start with y is equal to cosecant x. That gets us started. Now we're going to be shifted down 2, right? Because this should be here. This point should be here normally with no shifting, vertical shifting, but now it's down here, okay? Now, as far as vertical scaling, we can tell with secant and cosecant based on if there's vertical scaling, it will be indicated with where these minimums are and these maximums are. Now, you might say, well, okay, well, could we have scaled, we multiplied the y coordinate by -1, right? That's how we would go from, if this was normally here at 1, well, we scale about the y-axis by -1, and so we multiply every y coordinate by -1, and now this is here. Yeah, that's fine, but then all of these would flip too. In that case, we would be like this, right? So we couldn't have scaled about the y-axis by a negative number, because then all of this should be flipped. So this is the equation for the function. Okay, here we can see that it looks like this hasn't been shifted vertically, and we have a peak at pi over 3, and it's not starting at x equals 0. The curve doesn't start at 0 and go up, and also at x equals 0, it's not like it's starting at a peak point. So it looks like we're going to have to do a shift here with a sinusoid. And so what we can do is we can think about cosine would start here, right? We can shift a cosine curve to the right, pi over 3. So, okay. All right, now, do we need to scale the x, about the x-axis? No, the period's 2 pi. What about vertical scaling? No, the amplitude is 1, so that's it. Okay, this has the shape of tangent and the location as far as phase shift of tangent. So this is going to be a tangent. Okay, the period is 2 pi. From minus pi to pi, it's 2 pi. So the normal period is pi. So this has been scaled up. So we can write this up by a factor of 2, from pi to 2 pi, the period. Okay. Now, shifting, it looks like it's been shifted up by 1 as well. Right? Because this position here would normally be at 0, but now it's up at 1. Right? You don't have an x-intercept like this with tangent and cotangent unless, well, no, you do, but there's only that the x-intercept is like at the center of this shape. It's clearly here, it's like off center. That means because it's been shifted up. And that makes, instead of this point going through the x-axis, it goes through some, above or below the x-axis. So it's been shifted up by 1. Now, okay, let's see. Tangent of 0 is 0. Add 1, you get 1, but still that doesn't tell us if we had this, we'd still be at 1 anyway, so that doesn't tell us anything. Let's plug in pi over 2, because we're trying to see if there's any vertical scaling. So pi over 2 means we've got tangent of pi over 4 plus 1. We already saw tangent of pi over 4 is 1. So, okay, no vertical scaling, so there you go. Okay, so this looks to be a secant as far as the shifting is concerned. But with a secant, we should be seeing this in a standard way. It looks like it's been flipped about the x-axis. So we can start with minus secant x. Okay. Now, what about the period? We're going from minus pi to pi, 2 pi, so the period hasn't changed. All right. Now, we've scaled by 2, we can see. All right. Now, but looking at this position, this is normally 1 or minus 1. It's minus 2, so we want to scale about the y, the y coordinate by a factor of 2. And there we go. Well, wait, no. I'm sorry. Hold on. This looks more like a shift. Because, yeah, because if we just scaled by 2, then these would be here. Well, they wouldn't be, no, they'd be like here. We would see this. But that's not the case. So then it's been shifted down 1 minus secant x, so it gets flipped. It's flipped about the x-axis, secant is, and then it's just shifted down 1. So we've got minus secant x minus 1. There we go.